Late 1939, Santa Monica Airfield, Douglas Aircraft Company. The Douglas DC-4E prototype sits gleaming on the tarmac, registration NX18100 painted bold across its silver fuselage. For Pratt and Whitney twin Hornet engines, 1450 horsepower each, designed to revolutionize commercial aviation. Instead, this aircraft would become the foundation for one of Japan's most spectacular engineering failures. The goal, steal American heavy bomber technology. The mechanism, industrial espionage disguised as an airline purchase. The stakes, Japan's desperate need for a long-range strategic bomber to dominate the Pacific. The man walking toward the DC-4E wore the crisp uniform of Nippon Koku K.K., but his real employer was the Imperial Japanese Navy. His mission was simple in concept, treacherous in execution. Purchase this rejected American prototype and ship it to Japan for reverse engineering. What followed would expose the fundamental weakness in copying technology without understanding the industrial ecosystem that created it. Douglas Aircraft had spent 3 years perfecting the DC-4E, only to watch American Airlines reject it as too complex, too expensive, too ambitious. The tricycle landing gear was revolutionary. The pressurized cabin was decades ahead of its time. The 4-engine configuration promised range and payload that could span continents. But complexity came with a price American commercial aviation was not ready to pay. The Japanese, however, saw opportunity where Americans saw liability. Their aircraft manufacturers had spent decades building fighters and light bombers, but the vast distances of the Pacific demanded something far beyond their experience. The Imperial Japanese Navy's requirement was specific: a long-range attack bomber capable of carrying heavy loads of bombs or torpedoes a minimum distance of about 3,000 nautical miles. To meet this requirement, it became apparent a 4-engine layout would be necessary. Japanese aircraft manufacturers lacked experience in building such large, complex aircraft. The Navy was forced to search for a suitable, existing, foreign-made model upon which to base the new design. They settled on the American Douglas DC-4E Airliner. The purchase was arranged through Mitsui Trading Company, officially for use by Dai Nippon Koku. The cover story was elegant in its simplicity. Japan needed modern airliners to compete with Western carriers. The reality was industrial espionage on a massive scale. When the DC-4E arrived in Japan, the press received a carefully orchestrated story. The aircraft had crashed in Tokyo Bay during a test flight.
No survivors. Noreki recovered.
The story ran in newspapers across Japan, complete with quotes from fictional witnesses describing the terrible accident. The real DC-4E was being methodically dismantled in a secure hangar at the Nakajima Aircraft Company facility. Engineers worked in shifts, photographing every component, measuring every dimension, reverse engineering years of American aviation development. The wing structure was photographed from dozens of angles. The tricycle landing gear was disassembled and reassembled repeatedly until every mechanism was understood. The engine mounts were traced and retraced. Nakamura Katsuji led the reverse engineering project. He had spent 2 decades designing fighters for the Imperial Japanese Navy, but nothing had prepared him for the complexity of the DC-4E. The aircraft represented a quantum leap in engineering sophistication, with systems integrated in ways Japanese designers had never attempted. The electrical system alone required months of analysis. American engineers had routed hundreds of miles of wiring through the aircraft, creating redundant pathways that could maintain critical functions even if primary systems failed. The hydraulic system operated at pressures that pushed Japanese metallurgy to its limits. The flight controls incorporated servo assistance that reduced pilot workload but demanded precision manufacturing beyond most Japanese factories. The team worked through the winter of 1939 and into 1940, creating detailed drawings of every component. They reverse engineered not just the design, but the manufacturing processes required to build it. Tool marks on metal components revealed the types of machinery used. Rivet patterns showed assembly sequences. Paint layers indicated quality control procedures. By spring 1940, the team had generated over 10,000 technical drawings. They had identified the materials used in every component, from the aluminum alloys in the wing structure to the rubber compounds in the fuel lines. They had mapped the electrical system, hydraulic system, fuel system, and control system. But copying design was only the first challenge. Building the aircraft would require capabilities Japanese industry had never developed. The Nakajima team decided to retain the DC-4Es wing form and power plant arrangement, but adapt the fuselage for military use. They replaced the passenger cabin with a bomb bay capable of carrying about 8,800 pounds of ordnance. They added a glazed nose for the bombardier and defensive armament comprising two 20mm Type 99 Model 1 autocannon in dorsal and tail turrets, plus 77mm Type 92 machine guns in nose, ventral, and waist positions. The resulting design was designated G5N1, with the name Shinzen meaning Deep Mountain. The Imperial Japanese Navy classified it as the experimental 13 Sure attack bomber. The aircraft would be powered by 4 Nakajima NK-7A Memori 11 engines, each producing 1870 horsepower. On paper, the G5N1 looked impressive. It was broadly comparable in size to the later B-29 Superfortress, though considerably lighter. The maximum speed was calculated at about 260 miles per hour at 13,450 feet. The range with reduced bomb load was projected at about 2,700 miles. The service ceiling was estimated at 24,440 feet. The reality proved far different. Construction of the first prototype began in late 1940 at Nakajima's primary facility. From the beginning, problems emerged that American engineers had solved through years of experience Japanese manufacturers did not possess. The aluminum alloys specified in the American drawings required heat treatment processes Nakajima had never mastered. Early wing panels cracked during stress testing. The hydraulic pumps leaked because Japanese seals could not maintain pressure at American specified tolerances. The electrical system suffered cascade failures because Japanese wire insulation could not handle the heat generated by high amperage circuits. Each problem required engineering solutions that added weight, complexity, and cost. The wing structure was reinforced with additional frames, increasing empty weight by over 2,000 pounds. The hydraulic system was redesigned with lower operating pressures, reducing reliability. The electrical system was simplified, eliminating redundancies that American engineers had included for safety. But the most serious problem was the power plant. The Nakajima NK-7A Memori 11 engine was designed to compete with the most advanced radial engines in the world. At about 45 liters displacement, it was one of the largest 14-cylinder radials ever built, rivaling the American Wright R2600 twin Cyclone. The target output was 1870 horsepower, enough to give the G5N1 the performance the Navy demanded. The engine proved to be a disaster. Designed by Kiyoshi Tanaka, the Memori 11 suffered from fundamental flaws that plagued it throughout development. The cylinder heads cracked under thermal stress. The supercharger system failed to maintain boost pressure at altitude. The fuel injection system created hot spots that led to detonation. The cooling system could not dissipate heat generated by the massive displacement. Test runs rarely exceeded 30 minutes before component failures forced shutdown. When the engines did run at full power, they consumed fuel at rates that made the G5N1's range projections impossible. Maintenance requirements were staggering, with major overhauls needed after every few hours of operation. The Memori 11's unreliability was compounded by manufacturing quality that fell far short of American standards. Tolerances that American factories achieved routinely were beyond Japanese capabilities. Metallurgy that worked in American engines failed in Japanese copies. Quality control procedures that ensured American engine reliability were ignored or misunderstood. By early 1941, it was clear the Memori 11 would never meet specifications. But the Navy had committed to the G5N1 program, and Nakajima had promised delivery of the first prototype by spring. April 10, 1941, about 1,435 hours. The first Nakajima G5N1 prototype lifted off from the company airfield, marking Japan's entry into the strategic bomber era. The test pilot fought the controls as the aircraft struggled to climb, the 4 Memori 11 engines producing far less power than specified. The flight lasted 47 minutes. During that time, the number 2 engine overheated twice, forcing power reductions. The hydraulic system lost pressure, making the controls increasingly heavy. The electrical system flickered intermittently, causing navigation instruments to fail. When the pilot finally landed, he wrote in his report, "This aircraft is not ready for combat operations." 3 more G5N1 prototypes followed, each plagued by the same fundamental problems. The aircraft's performance fell short of every specification. Maximum speed in level flight never exceeded 240 miles per hour, far below the calculated 260 miles per hour. The service ceiling topped out at 19,000 feet, well below the specified 24,440 feet. Range with full bomb load was limited to about 1,200 miles, less than half the required 3,000 nautical miles. Naval Air Headquarters faced a difficult decision. The G5N1 program had consumed enormous resources and delivered an aircraft that could not meet basic requirements. Canceling the program would admit failure and waste the investment. Continuing development would require fundamental changes that amounted to starting over. They chose a middle path that satisfied no one. In an attempt to salvage the project, 2 additional airframes were fitted with 1530 horsepower Mitsubishi 4 billion Malawian kwacha's 12 Kase engines and redesignated G5N2S. The Kase was a proven power plant, reliable and well understood. It powered the successful G4M Betty bomber and had demonstrated its capabilities in combat operations. But the Kase engines produced 340 horsepower less than the failed Memori 11s, and the G5N2 was already overweight. The resulting aircraft was even more hopelessly underpowered than the G5N1. Test flights of the G5N2 variants revealed performance that bordered on dangerous. Maximum speed dropped to 220 miles per hour. The service ceiling fell to 16,000 feet. Range was limited to about 1,800 miles with reduced bomb load. The aircraft was too slow to evade fighters, too low to avoid anti-aircraft fire, and too short range to reach strategic targets. By late 1942, Japan was fighting for its survival in the Pacific. The initial victories at Pearl Harbor, the Philippines, and the Dutch East Indies had given way to grinding attrition as American industrial might began to tell. The Navy desperately needed every aircraft it could get, but the G5N program was consuming resources while producing aircraft unsuitable for combat. The decision was made to cut losses. In 1943, all 4 G5N2S were rebuilt as G5N2L transport aircraft. The bomb bay was converted to cargo space. The defensive armament was removed. The glazed nose was replaced with solid metal. The aircraft were redesignated Shinzen-Kai Model 12 Transport and assigned to the 1021st Kokutai at Katori Air Base. The conversion to transport role represented the final admission of failure. Japan had spent 4 years and enormous resources reverse engineering American technology, only to produce aircraft that could not perform their intended mission. The 6 G5N aircraft represented the largest industrial espionage operation in aviation history and a significant failure. The 1021st Kokutai operated the G5N2L transports in the unglamorous role of hauling supplies between Japanese bases. The aircraft's long range made them useful for flights to distant outposts, but their cargo capacity was limited and their maintenance requirements enormous. Ground crews at Katori Air Base struggled to keep the complex aircraft operational, often cannibalizing parts from one aircraft to repair another. Flight crews who had expected to pilot Japan's first strategic bomber found themselves flying cargo runs to bypass garrisons. The missions were dangerous but not heroic, ferrying medical supplies to isolated atolls and evacuating wounded personnel from forward bases. The G5N2L crews knew their aircraft were failed bombers pressed into service because Japan had no alternatives. Lieutenant Commander Suzuki commanded the 1021st Kokutai through the final years of the war. His unit operated 4 G5N2L aircraft and struggled constantly with maintenance problems inherited from the bomber design. The Mitsubishi Kase engines were reliable, but everything else about the aircraft reflected the complexity that had doomed the bomber program. The hydraulic system required specialist attention that few Japanese mechanics understood. The electrical system developed mysterious faults that could ground an aircraft for weeks. The tricycle landing gear, revolutionary when designed for the DC-4E, proved fragile under military conditions. Most seriously, spare parts were nearly impossible to obtain as the war situation deteriorated. By 1944, only 2 G5N-2L aircraft remained operational. One was destroyed in an Allied bombing raid on Katori Air Base. Another was cannibalized for parts to keep the remaining aircraft flying. The final 2 aircraft continued operating until the war's end, a testament to the dedication of ground crews who kept flying impossible aircraft through impossible circumstances. American intelligence officers had been tracking the G5N program since 1941, when reconnaissance flights over Japan photographed unfamiliar aircraft at Nakajima facilities. The 4-engine configuration and size suggested a strategic bomber, leading to the assignment of the reporting name Liz. Intelligence analysts prepared detailed briefings on the threat posed by Japan's new heavy bomber. The reality proved anticlimactic. Liz never appeared over American targets. No G5N aircraft participated in combat operations as bombers. Intelligence reports gradually shifted from tracking a dangerous new weapon to documenting an apparent failure. When Allied forces occupied Japan in August 1945, investigation teams were dispatched to locate and examine captured aircraft. At Atsugi Air Base, investigators discovered an intact G5N-2L transport sitting abandoned on the ramp. Technical intelligence specialist Major Robert Chun led the examination of the captured aircraft. His team had investigated dozens of Japanese aircraft, but the G5N-2L presented unique insights into Japanese industrial capabilities and limitations. The basic design is sound, Chun wrote in his initial report. The wing structure shows sophisticated understanding of aerodynamic principles. The control systems demonstrate advanced engineering. But the execution reveals fundamental manufacturing limitations that doomed the program. Chen's team discovered rivets that failed to meet dimensional tolerances. They found electrical connections that showed signs of overheating. They documented hydraulic fittings that leaked because Japanese seals could not maintain pressure. Most telling, they found maintenance logs that recorded constant component failures and repairs. The power plant examination revealed the scope of Japanese engine problems. The Mitsubishi Kase engines in the G5N-2L were well made and reliable, but they were also 340 horsepower short of what the aircraft needed. The Nakajima Memori 11 engines from scrapped G5N-1 aircraft showed evidence of chronic overheating, detonation damage, and manufacturing defects. The Japanese attempted to leap from light bomber engines to heavy bomber power plants without developing the intermediate technologies. Chun concluded. They copied the Douglas DC-4E structure but could not replicate the engineering ecosystem that made it work. The G5N investigation became a case study in the limitations of reverse engineering. Japanese engineers had successfully copied the DC-4E's design, but they could not replicate the manufacturing processes, quality control procedures, and industrial infrastructure that made the design viable. American aluminum alloys had specific properties that required precise heat treatment. Japanese attempts to substitute available materials resulted in structures that were heavier, weaker, or both. American electrical systems used insulation compounds developed through years of research. Japanese substitutes failed under heat and vibration. American hydraulic seals used rubber formulations optimized for high-pressure applications. Japanese alternatives leaked, hardened, or swelled. Each substitution added weight, reduced reliability, or compromised performance. The accumulated effect was an aircraft that looked like its American inspiration but performed like a caricature. The engine problems were even more fundamental. The Nakajima Memori 11 represented Japan's attempt to match American engine development without understanding the metallurgical advances that made high-power radials possible. American engines used steel alloys that maintained strength at high temperatures. Japanese metallurgy could not replicate these materials, leading to cylinder heads that cracked and connecting rods that failed. Fuel injection systems in American engines were calibrated to precise tolerances using equipment Japanese factories did not possess. Ignition systems used components made to specifications Japanese manufacturers could not achieve. Cooling systems required heat dissipation capabilities that Japanese designs could not provide. The Memori 11's failures cascaded through the entire G5N program. An underpowered aircraft could not meet performance specifications. An unreliable power plant could not complete test programs. An engine that required constant maintenance could not support operational use. By war's end, the G5N program had produced 6 aircraft, none of which served effectively in their intended role. Japan had invested enormous resources in reverse engineering American technology, only to discover that copying design was vastly different from replicating capability. The technical intelligence teams found evidence of other Japanese reverse engineering projects throughout their occupation duties. Captured documents revealed systematic efforts to acquire and copy American, British, and German technologies. Some projects succeeded brilliantly, producing aircraft like the A6M0 that dominated early Pacific air combat. Others failed spectacularly, like the G5N program that consumed resources while delivering unusable aircraft. The difference lay not in the quality of Japanese engineering, which was often excellent, but in the industrial ecosystem required to transform designs into effective weapons. American aircraft succeeded because they were supported by metallurgy, electronics, chemistry, and manufacturing infrastructure developed over decades. Japanese copies failed when they could not replicate this supporting infrastructure. The G5N program's failure was particularly ironic because Japan possessed the engineering talent to develop effective heavy bombers. The later G8N Renzen, designed from scratch rather than copied from foreign aircraft, showed promise before being cancelled due to resource constraints. Japanese engineers understood aerodynamics, structures, and systems. What they lacked was the industrial base to manufacture complex aircraft reliably. The Douglas DC-4E that inspired the G5N program eventually found success in its original form. Douglas used lessons learned from the complex prototype to develop the simpler, more reliable DC-4, which became one of the most successful transport aircraft in history. Over 1,100 DC-4s were built, serving with airlines and military forces worldwide for decades. The G5N program, by contrast, produced 6 aircraft that never achieved their design goals. 2 were cannibalized for parts. 1 was destroyed by bombing. 1 was abandoned at Atsugi Air Base. The fate of the other 2 remains unknown, presumably scrapped when their maintenance became impossible. The story of Japan's attempt to copy America's 4-engine bomber technology reveals the complexities of technological transfer in wartime. Industrial espionage could acquire designs, but it could not replicate the knowledge, skills, and infrastructure that made those designs work. The Japanese discovered that stealing American technology was easy compared to making it function effectively. The DC-4E that arrived in Japan in 1939 represented years of American engineering development. The G5N program that followed consumed 4 more years of Japanese engineering effort. At the end, Japan had spent 8 years and enormous resources to produce aircraft inferior to what American designers had rejected as unsuitable for commercial service. The irony was profound. American airlines had rejected the DC-4E because it was too complex, too expensive, and too ambitious for commercial operations. Japanese military planners embraced the same design because it promised capabilities their forces desperately needed. Both assessments proved correct. The DC-4E was indeed too complex for the Japanese industrial base to manufacture effectively, and the G5N program was indeed too ambitious for Japan's technological capabilities. In the end, the G5N program demonstrated that copying technology requires more than obtaining blueprints. It requires understanding the industrial ecosystem that created the technology, replicating the manufacturing processes that make it work, and developing the support infrastructure that keeps it operational. Japan learned this lesson at enormous cost, producing one of history's most spectacular examples of reverse engineering failure. The abandoned G5N2L at Atsugi Air Base became a monument to the limits of technological espionage. American investigators photographed it extensively before it was scrapped, documenting the final chapter of Japan's attempt to steal its way to strategic bombing capability. The aircraft sat on the ramp where its crew had parked it in August 1945. Engines cold, fuel tanks empty, mission incomplete. 4 years after its first flight as a prototype heavy bomber, the G5N had ended its service life as a transport aircraft in a defeated nation. The dream of Japanese strategic air power had died with the Nakajima Memori 11 engines that could never deliver their promised performance. Major Chen's final report on the G5N program concluded with an assessment that captured the essential lesson. The Japanese demonstrated remarkable skill in reverse engineering American designs, but they underestimated the industrial infrastructure required to make those designs successful. Copying technology is not the same as understanding it, and understanding technology is not the same as manufacturing it effectively. The G5N program had begun with stolen American technology and ended with failure. Japan had attempted to shortcut the long process of developing heavy bomber capabilities by reverse engineering proven designs. Instead, they discovered that technological superiority could not be stolen, only earned through the patient development of industrial capabilities that supported advanced engineering. In the larger context of World War II, the G5N program's failure had strategic implications. Japan entered the war believing that superior spirit and tactical innovation could overcome material disadvantages. The G5N program demonstrated the limits of that philosophy. When faced with complex engineering challenges, there were no shortcuts to success. American industrial capabilities that had taken decades to develop could not be replicated in a few years of reverse engineering. The Pacific War would be decided by industrial production rather than individual heroism, by manufacturing capability rather than tactical brilliance. Japan's failure to develop effective strategic bombers was one symptom of broader industrial limitations that ultimately determined the war's outcome. The story ended where it began, with American technology and Japanese ambition. But the DC-4E that had arrived in Japan with such promise in 1939 had spawned a program that consumed enormous resources while failing to achieve its goals. Japan had learned that stealing America's best aircraft technology could not overcome the fundamental industrial advantages that made that technology successful. The G5N program stands as a cautionary tale about the limits of reverse engineering and the importance of indigenous technological development. Japan's engineers were skilled and dedicated, but they could not overcome the industrial ecosystem advantages that made American aviation technology successful. In the end, they discovered that building copies of advanced aircraft required more than acquiring blueprints. It required replicating the entire industrial infrastructure that made those aircraft possible. The final lesson of the G5N program was written in the abandoned aircraft at Atsugi Air Base, silent testimony to the failure of technological theft. Japan had stunned itself by discovering that stealing America's best aircraft technology had produced their worst bomber, a failure that epitomized the broader industrial challenges that shaped the Pacific War's outcome.